Welcome to the fourth video in chapter 14 of the Crystal Clear Electronics video series.
In this part, we will compare two analog signals with each other and control an output according to their relation. Let's name the two analog signals. One of them is a known voltage called reference voltage, and the other is the unknown voltage called test voltage or the input voltage. In the circuit, always consider the reference voltage as a constant value and the test voltage or input voltage as a varying value.
Korábban ismertetett 12 voltos akkumulátorteszttel kapcsolásban a referenciafeszültség a Zener-diódák letörési feszültségét
and the base emitter forward voltage of the transistor, which is 6.6 volts, whereas the input voltage is half the supply voltage.
fele volt. Ennek a két feszültségnek
We will examine the relationship of these two voltages with a circuit further on, where the goal will be to decide whether the input voltage is higher or smaller than the reference voltage.
az ábrán látható
The figure shows how the levels of the input and the reference voltage affect the output voltage.
a LED fényerejére.
The battery testing circuit from the previous section has some faults, due to the fact that the voltage on the Zener diodes will change slightly if the current changes.
Áramerőssége akkor kismértékben, de változik a rajta.
Also, the base emitter voltage where the transistor turns on is not a constant value either, and it depends on environmental factors too, for example the temperature. In other words, the reference voltage is not constant.
Ebből arra következtethetünk,
This means that with this design, we cannot get a sharp comparison between the two voltages, which could be used to toggle the output, in this case the state of the LED.
ezen felül további
Another problem is that the tested voltage source is loaded by the current needed to drive the transistor.
meghajtásához kellett.
In summary, the earlier circuit needs to be improved because the output status change is gradual, not instant, and the circuit loads the measurement circuit with relatively high current.
However, I already really like this circuit. Do you have any ideas on how we can do it differently?
Igen,
Yeah, luckily there's a better way.
megoldás is. Két analógiát összehasonlítás.
There exists a dedicated component for comparing analog voltages that does not suffer from these issues. It's called a comparator.
Megnevezésű céláramkört. Ezen felül
Several microcontrollers contain comparator peripherals as well, which can compare an unknown input signal to a reference voltage. In this video, we would like to introduce a new component called the hysteresis comparator. But before that, we must first understand how operational amplifiers work, and we need to learn some new terms. Operational amplifiers are manufactured in different types of packages. The most common packages are the DIP-8 and SO8, which have 8 pins. Some types contain several op-amp units inside a single package. In this case, they share a common supply voltage. From now on, we will talk about the TL081 op-amp. Its pinout can be seen on the figure. An operational amplifier has at least 5 pins. First, you will need a positive supply voltage, pin 7, and a negative supply voltage, pin 4.
az erősítőnek
The amplifier has two inputs. The positive input, which we usually call the non-inverting input, which is pin 3, and the negative input, which we call the inverting input, which is pin 2.
az erősítőhöz természetesen
The amplifier also has an output, of course, which is pin 6. We won't discuss the other pins here. For now, this knowledge will be enough. For more information on the functions of the pins of a particular type of operational amplifier, please refer to the component datasheet. An operational amplifier drives its output based on the voltage difference between its positive and negative inputs multiplied by a constant. This constant number, represented by A0 in the formula, is the gain of the operational amplifier. The exact value of the multiplier constant depends on many parameters, for example the type and temperature of the operational amplifier. It's usually between 10,000 and 1 million.
ez azt jelenti,
But this would mean that if the voltage difference between the two inputs is 1 volt, the output voltage should be between 10,000 and 1 million volts.
és 1 millió volt között kéne legyen.
I don't really want to go into detail, but it seems to me that this is not possible.
That's true.
Feszültséget a pozitív,
The output voltage of an op-amp is limited by its positive and negative power supply.
a negatívnál nem.
When the output reaches one of the supply rails, we call it saturation. So, with a 1 volt difference between the two output terminals, with the positive input terminal having a higher potential, the output voltage would saturate and equal the positive supply voltage. Some operational amplifiers' output can't fully reach the supply voltage, which means that the maximum output voltage is slightly less than the positive supply voltage, and the minimum is a bit more than the negative. The types whose outputs can reach the supply voltages are called rail-to-rail operational amplifiers. The TL081 is not a rail-to-rail op-amp. The TL081 is not in the official component list, so the following circuit is presented only as a theoretical demonstration of this phenomenon. Here are the inverting and non-inverting inputs, the positive and negative supply voltages, and the output. A resistor divider is used to divide the supply voltage by 11, so we can measure a voltage of around 1.2 volts at the non-inverting input. Then, on the output of the operational amplifier, you can measure a slightly lower voltage than the supply voltage.
Now, hold on, wait a minute. What we need now is a comparator. Can you tell us how to turn the operational amplifier into a comparator?
Of course, it will be clear in a moment. Comparators are used to compare two analog input signals. Usually, you want to compare a known voltage, the reference voltage, with another voltage. If we connect the reference voltage to the inverting input of the operational amplifier, and the voltage to be compared is connected to the non-inverting input, then the output voltage of the operational amplifier is as follows. The output will be at the positive supply voltage if the compared voltage is higher than the reference voltage. The output will be at the negative supply voltage if the compared voltage is lower than the reference voltage. This means that the output voltage of the operational amplifier shows whether the compared voltage is higher or lower than the reference voltage, meaning that this circuit is a comparator. Comparators that are available in stores are such operational amplifiers that have beneficial parameters when used as comparators. However, if we use them as operational amplifiers, they have some suboptimal features. It's important to remember that operational amplifiers are mainly used for amplification, and comparators are mainly used to compare voltage signals. In terms of their basic operation, there is no difference between them. In schematics, the comparator and operational amplifier are usually marked with similar symbols. If a comparator is explicitly marked, it is usually as shown in the diagram.
Can you talk a little bit about the different types of comparators?
But of course, for example, there are window comparators, comparators without hysteresis, and comparators with hysteresis. The window comparator indicates on its output whether the input voltage falls in the range between the two threshold levels, that is, a voltage window. The comparator without hysteresis is the simple comparator which we have described previously. Comparators with hysteresis are very similar to regular comparators, but after their output changes, a slightly bigger change is required in the opposite direction to change them back. The difference between the two threshold levels is called the hysteresis voltage. We will deal with hysteresis in more detail in a moment. In reality, comparators without hysteresis, available in stores, also have hysteresis, but their hysteresis voltage is usually so small that it's negligible. The output of a comparator can be viewed as a digital signal, with the value being a 1 if the voltage equals the positive supply voltage, and the value being a 0 if the voltage equals the negative supply voltage. We can build a comparator with a useful amount of hysteresis out of any comparator, but first, let's talk about why hysteresis is useful. Suppose that we want to control the cooling in a room with air conditioning. We set the temperature to 23 degrees centigrade. We have an analog thermometer, and we connect the temperature signal to a comparator, which has a reference voltage that corresponds to 23 degrees Celsius on the thermometer. We route the output of the comparator to the air conditioner, turning it on if the temperature is above 23 Celsius and turning it off if it is below that. Suppose that in the beginning, the room temperature is 30 degrees Celsius. The air conditioning turns on and starts to cool the room. When the temperature reaches 22.99 Celsius, the AC turns off. Because the cold airflow is stopped, the thermometer will instantly rise back above 23 Celsius, turning the AC on again, which in turn starts to blow cool air on the thermometer, cooling it down again, and turning the AC off. This results in the AC being continuously switched on-off all the time, which is not good for the unit. It would be much better if the AC would only switch back on when the temperature has risen significantly, for example above 23.6 Celsius, and we would also only switch the AC off when the temperature is below 22.4 Celsius, so that the warming room will stay around the desired 23 degrees centigrade longer. The difference between these two thresholds is exactly the hysteresis. Usually, hysteresis is required because in real life every measurement has noise. In other words, the measured value oscillates around the real value, and that would cause the output value to oscillate as well when the input is at the threshold voltage. The phenomenon is represented with this figure. We can imagine hysteresis as having two thresholds close to each other. If the input signal is smaller than the lower threshold value, then the output of the comparator changes from 1 to 0, and its output changes from 0 to 1 if the input signal is greater than the upper threshold value. If we choose the threshold values properly, then we can eliminate the fast on-off switching on the output resulting from noise. Back to cooling the room, let's say you're tired of the constant switching and decide to compromise and tolerate temperatures between 22 and 24 degrees and get a comparator with hysteresis. We set our comparator so that the hysteresis voltage corresponds to 2 degrees Celsius and the threshold voltage is at the voltage corresponding to 23 degrees Celsius. Let's start again at 30 degrees Celsius. The air conditioner will continue to operate until the room cools to 22 degrees Celsius, at which point the air conditioner will switch off. The temperature will rise, but the air conditioner will not switch on at 23 degrees Celsius, but only at 24 degrees Celsius. We have achieved what we wanted. No continuous switching, but we can continue reading the chapter on comparators at a comfortable temperature.
So far, that sounds very good. Can you show us how to make a comparator with hysteresis out of a regular comparator available in the shop?
The circuit is simple. We only need a comparator and two resistors. The two resistors connect the output of the comparator to the positive input, as shown in the figure, creating a positive feedback loop. This way, the output affects the input, and the bigger change is needed on the input side to tilt the output of the comparator. The hysteresis voltage can be calculated using the following formula. The higher comparing threshold is calculated using the following formula. As you can see, its value depends on the value of the reference voltage, the value of the output voltage, and the value of the resistors. The lower comparing threshold is calculated by the following formula. As we can see, the reference voltage and the value of the resistors are also included here, but instead of the value for the negative output, the value for the positive output is used in the formula.
If I'm thinking correctly, we can build a cooling switch of the room. What exactly do we need?
We'll need a thermometer, which converts the temperature to voltage, a hysteresis comparator, a potentiometer to be able to adjust the desired temperature of the room, and the reference voltage, which can be implemented simply with a voltage divider made of resistors. You can see the circuit in the figure. An unusual property of the type of comparator used is that it can only pull its output to the negative supply voltage, but not to the positive. This can be fixed by using the pull-up resistor R5, so that in logic 1, the output is pulled to the supply voltage through the resistor, and in logic 0, the comparator pulls the output to the ground. Such an output is called an open collector output. The reference voltage is defined by the supply voltage and the voltage divider formed from R3 and R4. Using this formula, the reference voltage is 9.2 volts. Substituting the value of the resistors and the reference voltage into the formula gives the high comparing threshold. It is 10.1 volts. To determine the high comparing threshold, substitute the value of the reference voltage that we just calculated and the low output voltage, which is currently 0 volts, into the previous formula. The result is 10.1 volts. To get the low comparing value, substitute the high output voltage, which is 12 volts, into the same formula. It gives the value of 8.92 volts. Let's review the operation of the circuit as if the R6 resistor was not installed. The NTC and potentiometer form a voltage divider. The resistance of the NTC increases as the temperature decreases, and because of that, If we don't rotate the potentiometer, the voltage on the comparator's negative input rises. If this voltage rises above the high comparing threshold, in our case above 10.1 volts, then the comparator connects its output to the negative supply voltage, that is, the output voltage will be 0 volts. As a result, the MOSFET is turned off, so the fan won't spin. After this, if the temperature starts to rise, a reverse process takes place. The resistance of the NTC starts to decrease, so the voltage of the comparator's negative input starts to decrease as well. If it goes below the lower comparing threshold, in our case below 8.92 volts, then the comparator gets into a logic state 1. It disconnects its output from the negative supply voltage. Current, in this case, doesn't flow through the R5 resistor, and voltage doesn't drop, so the voltage of the MOSFET's gate rises till it reaches 12 volts. Because of this, the MOSFET turns on, which means that the fan starts to spin.
So far, this is perfectly understandable, but you haven't mentioned the role of the R6 resistor. Why this might be even necessary?
It's important to notice that the MOSFET's maximum permissible gate source voltage can be different for each type. Always make sure that you never exceed the limits which are in the datasheet. In our example, the NTD 4963N MOSFET's gate source voltage can be between plus minus 20 volts. In the circuit, the gate source voltage varies between 0 volts and 12 volts, so we meet the requirements. If you use a MOSFET where the maximum gate source voltage is lower than 12 volts, then the R6 resistor is needed so that when the comparator disconnects its output from the negative supply voltage, the MOSFET's gate source voltage will be only around 6 volts because R5 and R6 form a voltage divider and the resistances are the same. R6 has to be chosen so that the voltage on it should be always smaller than the maximum allowed voltage of the MOSFET's gate source voltage.
You can test the circuit if you adjust the potentiometer in its steady state until the fan stops spinning. After that, if you warm up the NTC with your hand, the fan has to turn on. If you stop warming it up in a short amount of time, then the fan has to turn off again. You can replace the fan with an LED as an example, but don't forget to connect the proper valued resistor in series with it. I think we have learned a lot of new things in this video too. If you didn't understand something for the first time, don't be disappointed. Watch the video again, pausing where necessary. See you in the following video.
Bye!